Hi everyone, I'm Mohana, a master student at IT Mandi, and I'll be presenting our work on learning-based practical light field image compression using a disparity-aware model, co-authored by Dr. Renu Rameshan. The 4D light field captures a much richer representation of the light in our 3D environment as compared to traditional 2D imaging. In traditional 2D photography, the light coming off of a point on an object gets focused by the lens to a point on the sensor. So this captures the intensity coming off of the point, but there is an integration in the angular domain, so we lose the directional information of the light rays. Light field cameras, on the other hand, are equipped with a micro lens array, which helps to separate out the light rays. So this captures not only the intensity, but also the direction of light. In our work, we make use of the multi-view representation of the 4D light field, where you can see the spatial variation across the U and V dimensions and angular variation across the S and T dimensions. Now, owing to the additional information captured in 4D light field, it enables an array of exciting applications, but it also causes a much higher data load, making the compression of light field images of an immediate concern. And over the years, multiple solutions have been proposed for compression of light field images. Most of them have been inspired by the developments in the traditional image and video compression fields and make use of standard existing hand-designed codecs like HEVC and JPEG. In recent years, with the rising popularity of deep learning in many fields, the field of image compression is also seeing a new direction of development. The light field compression community has also seen a number of efforts in using learning-based approaches. However, most of these models are made up of a number of separate components and make use of existing standard hand-designed codecs like HEVC to achieve different bit rates, followed by a learning-based component to enhance the performance. This increases the complexity of the model, and some of the components are not really designed keeping in mind the specific quality and structure of light field. So in our work, we propose a new end-to-end model which learns to compress light field images by optimizing for not only the distortion but also for rate. Now, out of the entire 4D light field, we used only the center 8x8 views, and at a time our model works on one row of the entire 4D light field. So on a closer look, you would be able to number the views from 1 to 8. So essentially here we are converting the 4D light field into 3D. The overall structure of our model is that of a simple autoencoder consisting of an encoder which takes as input the 8 views of the input row and performs a nonlinear analysis transform to map the input to a lower dimensional representation, followed by the usual steps of quantization and entropy encoding. The bitstream then is entropy decoded on the decoder side, and the decoder then performs a nonlinear synthesis transform to recover the reconstruction. Implementing a naive approach like this, however, is not enough to capture the complex structure of light field data. So we break the model into a number of smaller components and inject some common sense into the model. The two main components of our model includes a color module and 8 auxiliary disparity modules. The color module takes as input the 8 views of the input row, and to take advantage of the spatial correlation as well as the angular correlation, the module is made up of 3D convolutional layers along with some nonlinearities. And as the name suggests, the color module should learn the intensity information of the light field input. The auxiliary disparity modules, on the other hand, should learn the disparity information. So the ith disparity module works on the ith column of the input row. So the input tensor to this disparity module consists of 4 slices. The first slice is the ith view of the current input row. The second slice is the center view, where we are taking the fifth view as the center view, and the other two slices contain the position indices of the ith view with respect to the entire 4D light field. So for the second disparity model, and if the input row was the first input row, the first slice would be x1, 2, and s would be 2 and d would be 1. So going over the end-to-end training pipeline of our model, the input data is structured as described, and each of them go through their respective encoders to get a smaller encoded representation. This is followed by the usual steps of quantization and entropy encoding. Now, the entropy encoding uses fully factorized priors, and the prior used by the color module is different from the prior used by the disparity modules. And the priors are also shared with the decoders beforehand. The resulting bit streams are packed into a single bit stream along with all required overhead and transmitted to the decoder. On the decoder side, the bitstream is unpacked and followed by entropy decoding using the shared prior to recover the encoded representations. These then go through their respective decoders, and on the color module side we have an intermediate representation of the output, whereas on the disparity module side we get 8 disparity maps. Each of the disparity map is used to warp their respective slice of the intermediate reconstruction, and this gives us the final reconstructed output. Now, since there are some learnable parameters of the model, we update the parameters values by optimizing for an objective function. So this is the rate distortion loss. The distortion here is given by a simple MSE loss between the final reconstruction and the original input. The rate is estimated using cross entropies, and this part comes from the color module, and these come from the 8 disparity modules. So PC here is the prior used by the color module, and PD is the prior used by the disparity module. Lambda is varied to achieve different bit rates. So for our experiments, we have used data augmentation by training on 64 cross 64 patches. However, testing is done on whole images. And our test set includes 18 light field scenes. This is the luminance MSSIM versus bitrate curve. MSSIM is in decibels and bitrate is in bits per pixel. And we have performed comparison against 3 standard hand design codecs, including JPEG 2000, HEVC, and VVC. As is shown, our model performs better than all 3. In terms of luminance PSNR, our model is not able to perform better than the video codecs. However, the performance is competitive and shows promise. Owing to the inherent structure of our model, we are able to take advantage of multiple GPUs to achieve practical encoding and decoding runtimes. So the table here shows the average processing time comparison with some of the recent learning-based models and VVC. So the time for our model is shown when we process 8 rows simultaneously. This is an example reconstruction from our model. The bitrate is around 0.2. As you can see, the model learns both the horizontal and the vertical parallax quite well. It also learns to reconstruct some of the trickier regions, like the occluded areas highlighted in this example. However, there are some color reconstruction artifacts, like in this example, the background shows some noisiness. There is also some blurriness. In some of the highly textured areas, there are some smoothing artifacts, as in this example. Now, as part of our ablation study, we have tried to use 2D CNN in our color module instead of 3D CNN. So the encoder uses only a center view while the decoder tries to decode all 8 views from the representation. Now, as expected, this gives a lower bit rate. However, the reconstruction quality is much blurrier. So on the left, it's from our 3D CNN color module, and on the right is from the 2D CNN one. The reconstruction at the discontinuities is also quite poor. There are some occlusion artifacts like missing pixels, especially for the views which are further away from the center view. There are also some noticeable boxing artifacts. Now, it is a well-known fact that deep learning models are data hungry, and the result is highly affected by the quality and quantity of data we can show. So we tried to test on the synthetic 4D light field dataset, and the results were not good. There was a lot of smoothing artifacts. As part of our ablation study, we also tried to train a single autoencoder without any disparity modules. Initially, we tried to train on whole images. Now, the reconstructions were very blurry, and the disparity was being learned in only one dimension, the horizontal dimension. So this could be due to the input-wise row structure of our model. So it learns the disparity of the row but cannot find the relation between the different rows. However, when we increase the amount of data by training on patches, the model's reconstructions are still blurry, but it learns the disparity in both the dimensions. Now, visually, the 4D synthetic light field dataset shows visual quality lower than the other datasets, but the PSNR achieved for this dataset is comparable to the other datasets. MSSIM values, on the other hand, were distinctively lower. So probably MSSIM is a better indicator of visual quality. This also suggests that we should perform subjective evaluation in addition to objective evaluation. To summarize, we have proposed an end-to-end trainable model which learns to optimize for not only pixel-to-pixel distortion, but also learns the structure of the input data without requiring any ground truth disparity maps or handcrafted features, and achieves competitive performance in terms of both reconstruction quality and speed. For future work, we will try to improve the color reconstruction quality and optimize for entire 4D light field at a time, which should help in reducing the bit rate. Thank you for your attention.